So thank you very much, Lars, for this very kind introduction, and thank you all for being here tonight with me. And it's really a pleasure for me to give a little bit back tonight, maybe. Hopefully, you'll feel like that after the talk. I've been coming here for 15 years to KIDP, and it's been a wonderful place. Many great ideas have been started here that in the end turned into experiments. Actually, some of the experiments you will see tonight. So what I want to tell you today is about realizing Richard Feynman's dream of a quantum simulator. And actually, this story has many, many facets. And so I would just like to start with the motivation of, why we're doing what we're doing, what it has to do with Richard Feynman's vision in the 1980s. And then I'll tell you how we're doing it. And that's kind of almost a separate story by itself, but you'll see they're kind of very intertwined. So it's an interesting connection. And you actually see it goes way back to physicists like Einstein, de Broglie, Schrödinger, all our heroes in quantum mechanics and physics that we have. So I'll tell you about that, and finally I'll conclude with a few applications of what you can do with these things. All right, so let me start with the motivation of why we're doing what we're doing. So really, one of the most fundamental challenges in quantum physics today is not only to derive, what are the fundamental laws of nature. That's what the high-energy physicists do. They try to find, with microscopic probes, better and better ways to understand the laws by which microscopic particles interact and find new particles, but also to try to understand what I call the sociology of those particles. How, once you have the laws, when they have put many of them together, what kind of behavior do they show? What kind of collective behavior do they show? What forms of matter do they show? Do they become a metal? Do they become a solid? Do they become a superconductor? Things we'll hear about in continuous of the talk. So, and this is a lot of relevance, and it's, I would say, as difficult as the problem of finding these new particles and new interactions. So trying to understand how they act together and kind of what kind of phenomena we can get out of these. Of course, this has enormous technological relevance as well. A lot of these materials we use in computers today, in sensors, we hope to use them in next generation so-called quantum technologies, where we try to exploit these quantum mechanical effects, these enhanced materials, to build better sensors, better clocks. We'll talk about that, maybe quantum computers and things like that. But at the fundamental level, and that's what my interest is, the interest of my group mainly, is to try really to understand the underlying processes and really try to build model systems which allow us to do this in a very unique way. Okay, so why is it so hard? Why can't we just calculate this with our best computers? I mean, we have fantastic classical computers today, supercomputers costing a huge amount of money. So why can't we just put those, calculate what kind of material properties we're going to get? And let me explain what the problem is. So imagine what I call the ultimate hard drive, where you would store, encode within a single atom, you would encode a bit, a 0 and 1 of information, and that would be just this atom, for example, this spin as we have, as this arrow connected pointing upwards or downwards. Okay, that's a property of the atom that atom has, and now let's say all the atoms are in state 0, now all the atoms are in state 1, or there's some information stored on your hard disk, so it would correspond to some pattern of this information up and down, zeros and ones on your hard drive, right? Okay, so that's the classical world, but in the quantum world, we have a kind of intriguing feature that a quantum system can not only be in this state, or that state, or that state, or that state, it can be simultaneously be in all of those states. And when we even just want to write down what the state is, the system is, we need 2 to the n, where n is the kind of number of particles I have in my system, configurations. I have 2 to the n coefficients that I have to write down just to describe the state. I haven't even yet done any calculation with that. So just to give you an impression, 2 to the n is going to be, that's an enormous number, even if I just put 300 particles. 300 atoms is nothing compared to how many atoms we have in this piece of block of solid here, okay? So 300 atoms, absolutely nothing. But that's already a number which is as large as the number of protons we estimate to be in the entire universe today. So it's a gigantic number, okay? And that you haven't even done any calculation. That just to store those values, just to describe that state, is an incredibly complicated task. So this is the problem, that even with our best computers that we have at hand, even for very small system sizes, we run in this problem, we call this exponential increasing problem, that even if we want to add just one particle more, we want to calculate what the system does. When we go from 300 to 301 particles, we have to double the capacity of our computer. Okay? Every time we just add one more, we double. And that, of course, you can immediately see makes you run into a tremendous problem. That really does not allow you to calculate these problems in their full breadth on these supercomputers. And it's a fundamental problem. It's not a problem that we can solve in a few years with better computers. We can maybe go from 303 to 310 maybe, but that's not a huge advance in the problems. So here's where this other line of thinking comes in, and where we're going to connect to Richard Feynman. And it builds on really fantastic experimental work over the past decades in trying to control the quantum world, control single particles at the ultimate limit of what quantum mechanics allows us to do. For example, single atoms and ions, photons, and two of the heroes who received the Nobel Prize for their work on that were Dave Wineland here in Boulder and Serge Haroche in Paris, for example, who really were one of the pioneers who gained these ultimate control. So the amazing thing was that Richard Feynman already foresaw in the 1980s that if you would have such fantastic control, if you would ever have such control over such single quantum objects, and at that time we didn't, nobody had that control, so it's really quite visionary, then you could build something, build kind of a machine out of these, assemble out of these individual quantum objects a machine, a quantum simulator, some people call it a quantum computer today, to simulate this physics problem efficiently, without running into this huge problem, of this memory capacity problem that we heard about. And now there are actually many groups that try to solve this problem, try to address this. So I'll tell you about our work of these atoms and crystals of light. There are people working with these ions, so charged atoms that are held in electromagnetic cages. And actually also here a very successful group led by John Martinez here at UCSB and Google Labs here in Santa Barbara. They're trying to build these machines with superconducting devices. Okay, so that's the motivation. And now let me tell you how we do it. Okay, how we kind of generate the systems that allow us to build these quantum simulators. And now let me turn to the story of ultra-cold quantum gases. And this is another, almost like a separate storyline, as fascinating as the first one, but as I promised you, we'll connect them in the end, which starts in 1924, 1925, when a young Indian physicist, Satyendranath Bose, sent his work on black body radiation, a big problem at the time, to Albert Einstein, that Albert Einstein could translate the paper, because at that time, most of the physics literature was published in German. So you see, most of the famous physics literature was published in German, and he asked Einstein for help, and Einstein helped him, but also immediately saw that really this Indian physicist had a tremendous idea, and built on that idea, and wrote down his own theory later on, this quantum theory of the monoatomic ideal gas. So probably that's not the most famous work of Einstein, but it is actually a really important, one of his really important works in 1925. And we'll talk about what's so radical in this and why this is such a fantastic paper that he wrote in 1925. And it took almost 75 years more to realize this state of matter in its clear form. And the three heroes who did that in the end were Eric Cornell, Carl Weyman, and Wolfgang Kedderle, who shared the Nobel Prize for that in 2001. I'll explain exactly what I mean by that, what they actually did. And one thing I just want to show, this is a lab book excerpt of Wolfgang's lab books. Now we have it electronic, but at that time I also did my lab books handwriting. And you see, you have the time when things kind of happen. And so here's 5:54. 5:59, and that's 5 o'clock in the morning. Okay, so they measured the whole night, as we when it's the best conditions, always during night. So, and then you see at 6:04, 29 seconds, they see this BC exclamation mark. And that's what I want to tell you about. Actually, today I would also like to remember another hero who sadly passed away just 2 weeks ago, Deborah Jin. She was actually the one who tamed another kind of species, brought them into the ultra-cold world, and she deserves to be on this list just as much as these three here. It's a tragic loss for our whole community, but what I want to kind of show you in the next slides, why we are so proud of these four people. Okay. So it goes deep, actually touches deep on how we perceive matter when we talk about matter. What is matter? And here's a picture how most people would conceive matter, think about matter. So it's this we take a block of material. This is actually sulfur particles on a copper surface. A picture taken with a scanning tunneling microscope by another Nobel Prize winner, Gerd Binnig in Munich at the time. And so what you see looks like this is a sulfur atom, here's another sulfur atom, and they form this crystalline structure, and it looks like you have classical balls sitting there, particles, and they arrange in this crystalline structure. Okay, so it's a very classical picture in a sense of how matter should behave, how matter forms. But then again, quantum mechanics tells us otherwise. Quantum mechanics tells us that we should be thinking about matter as waves. We'll talk about waves in a second. So we should associate with each material particle, each one of us should be described by a wave. And how these waves propagate in space, how they behave, how they interact particles, this is described by the famous Schrödinger equation, describing how these waves, described by this psi symbol, how they actually behave. So what are these waves? So waves are periodic oscillations in space and time. So you have a crest here. If you kind of go to another space, you find another crest, and the separation between those two crests is called the wavelength. And if you sit in a fixed point in space and the wave goes up and down, water wave, for example, imagine that's the period of the wave, and we call that t here. And these are connected to each other, the wavelength and the period. They can, together with them, we can form how fast these waves actually propagate in space. Now, waves have a kind of interesting property that is a little bit non-intuitive that we need to understand. That's going to be fundamental to everything in the talk. So usually when we have matter, this sand pile here, and we add another sand pile to it, okay, we get twice as much sand. Okay, that's what we get. With waves, it's different. Okay, with waves, it depends really how you add them up. If you have a wave crest coming together with another wave crest, the wave gets amplified. Okay, the wave gets even stronger. But if a wave crest hits another wave which has a trough, then actually the wave can cancel out, and there's absolute standstill. So adding waves, putting two waves together, doesn't give you twice as much, but sometimes it can cancel out. And that's what we call interference. So sometimes you get enhancement of the wave, sometimes you get kind of destructive interference where suddenly everything stands still. And that's, of course, things we use whenever you put on your Bose acoustic noise canceling headphones. This is what you're making use of, that you're kind of having destructive interference at your ear of the surrounding sound around you that you're canceling out. Okay. So now let me show you a few wave phenomena, and because I guess you don't want to solve all these equations, these wave equations, there's this fantastic program you can download for Mac. I think for PC there must be a similar program too. It's called Ripple Tank. And it's really great because it allows you to look at many of the wave phenomena that can occur and understand them in a very intuitive way. Okay, so here is just, we're just dipping our finger in the water, okay, periodically at this point. And then the water waves are running out. Okay, waves propagate out from this source point that we have here. If we put two sources, let's dip our finger into the water in two places, you see something interesting happens. So there are regions in space where these waves get enhanced, but there are also regions in space where there's complete standstill of the water, and that's the interference I talked about. Okay, so when waves can cancel out. And actually, if you've asked yourself, let me show you this. If you've asked yourself why a wireless router actually has many of these, why does it have these many antennas? One reason why it has these many antennas is you want to optimize the direction how electromagnetic wave reaches you, where you are. You don't want it to broadcast the Wi-Fi signal to somewhere where you're not. You want it to reach you. And without having any mechanical rotation, you can do that. So you have these two emitters. These are these two antennae, which in your Wi-Fi router emit your electromagnetic waves. And what you're changing is actually how synchronously you're dipping your finger or you're exciting the waves at those 2 points in space. Are you doing it synchronously or out of sync or with a different phase, how we call it? And what's interesting, if I change this phase difference here, you see I can change in which direction this signal gets very strong. Okay? And that's what your Wi-Fi router is doing. So if you're here, it would send the signal, beam the signal to you there. Okay? If you're let's say back down more down in the house, it would do that, or something like that. Okay? So that's how that works. It's a beautiful program. I really encourage you to play with it. It has also it's like a mirage. This is a beautiful example how a mirage works. Okay, so you have a temperature gradient in the air. You have thin air here, hot air above, cold air here, and you can see how a wave can propagate from here to here, even around an obstacle. Okay, and create a mirage image. Okay, and there are many more things, so just go ahead, download the program. It's really a lot of fun, and you don't have to solve the equations. You can just enjoy the solutions that somebody calculated for you. Okay, so now we have to understand when can we actually perceive, when is this wave character actually important? So when do we really have to talk about waves, and when can we forget about the wave character? So typically the reason when we can think about waves and when not is a question of what is the wavelength of this wave. Remember, that's how a crest follows a crest, at what distance a crest follows a crest. How that's related to the size of the object it interacts with. For example, this laser beam emits electromagnetic waves, light waves, but of a tiny wavelength compared to, let's say, the structures in this building, the size of the door, the spacing of the door. So if I would shine my laser pointer through the door, it would just go straight through the door, and somebody at the side, at the entrance of KITP, would not see anything about my laser pointer. Okay. However, if we do the same thing with sound waves, if I speak, you can hear me at the entrance of KITP. Okay, sound waves propagate around the corner. And why? Because sound waves have a much larger wavelength of around a meter, and when they hit the door, that's kind of the same size as the wavelength here. They do something what we call diffraction. They spread out, and they can reach me even if there's no direct line connection between me standing here and the emitter speaking over here. Okay, so the crucial thing is that we need to understand is in order to perceive waves, in order to see something of the wave character, we need to have size of the object be of the same size as the wavelength. Whenever the size of the object is much bigger than the wavelength of these waves, we're never going to see anything of this wave character, and we can just perceive it as kind of straight line propagation. Actually, another example to give you a famous example where you can hear this for yourself. Next time you hear a marching band coming around a corner in a city, you first hear the trombones or the basses because they're the low frequency, they're the long wavelengths. And then you hear the flutes when the flutes come around the corner, okay, because they don't make it. They have the short wavelengths, okay? So think about that the next time you hear a marching band. All right, so now about these matter waves. We said if we just strictly follow de Broglie and we just calculate using his formula what is the wavelength of these matter waves, and we take a football, for example, with a mass of 0.5 kilogram, we shoot it with 20 meters per second, and we just plug it into de Broglie's formula, and you see we get this ridiculous small number. Okay. So this is such a tiny number that we have no microscopes at all that can resolve such a tiny wavelength. And that immediately tells us that for this football, this wave description is completely irrelevant in our normal world. We just cannot perceive it. The wave is just too small. We just can't see it. However, if we take an electron, for example, an elementary particle, which is much lighter, it can propagate quite fast, then this is still quite small, but it's not so small that we don't have anything we can put in its path to interact kind of on the same wavelength. And then we can suddenly start to see this wave character. But I'll show you actually a trick how to make these wavelengths even bigger in the end, to make them even more pronounced, that we can see them even on macroscopic scales. Okay, so what is interfering in terms of matter waves? We said in light, there's these light fields that are interfering, that create these interference patterns of light. And in quantum mechanics, it is this psi wave function that we wrote down that propagates according to the Schrödinger equation that interferes. But otherwise, actually, you find that these phenomena are pretty much the same. But it's still striking to see this.
We are looking
let me
at
stop
the
this for a
detector
second.
on the monitor.
It's still striking to see this for matter waves, because it really means that matter, at some point in space vanishes, there's destructive interference, and at other points in space, you see more matter appearing. And here's a famous example from Tonomura in Japan in Hitachi labs that he took. So what he did was basically like two light waves interfering. He took two matter waves. So he just took a beam of electrons, of these microscopic particles, sent one of these beam of these electrons around the left, the other beam of the particles around the right, and then brought them together again. And it's like in the sandpile argument, you would think you put electrons, these microscopic particles from the left, hitting microscopic particles from the right. Well, then you just get more microscopic particles hitting the screen at that point. They add up. But that's not the case. They're waves, remember, and we can see that. So here we're going to see now where the detection of these electrons.
Bright spots appear here and there. These spots indicate individual electrons. Electrons are sent out only occasionally. Therefore, the chance of finding one electron in the microscope is very small, not to mention the chance of finding two. Since electrons are detected one by one as particles, we have to conclude that each electron must have passed through at random on either side of the biprism, thus creating a uniform distribution without any interference when accumulated. Under such conditions, do electrons form a uniform distribution? But look, we begin to see some fringes in the perpendicular direction that looks like interference fringes. Since this experiment lasted for more than 30 minutes, I have sped the movie up. Interference fringes are now clearly visible.
So you see, actually, even with these microscopic electron particles, you don't just add them up, you form these interference patterns where matter now destructively interferes. There are regions in space where no number of electrons hit, so electrons almost completely vanish, and regions in space where they hit with a high probability, where they occur with high probability. And actually, if you go look, apart from that, all these phenomena are very similar for light waves and matter waves. So here's, for example, comparing electron diffraction on a crystal to X-ray diffraction. So these are matter material particles, the electrons. X-ray is light, and you see it looks exactly the same. If you send it along an edge, a sharp edge, you get also these interference effects, and you couldn't tell what is the electron pattern or what is the light pattern. So these are exactly the same phenomena you see for waves. It's a pure wave phenomena that you see. Actually, another beautiful example I want to finally show you is this example from Don Eigler at Almaden Research Labs, not far from here, where he's building kind of violins, I would say, for matter waves. Okay, so in a violin, what do you want to do? You want to enhance certain sound waves, the good sound waves. You want to build a resonator to amplify the sound within the violin corpus. And what Don could do, he could basically move around atoms on the surface of a crystal. This is an individual atom, and he can pick it up and move it around and put it in a ring. And this is now the resonance corpus for the matter waves in the solid. We have the electrons in the solid, they're waves, and suddenly you see these waves get amplified. And you can really directly see the wave character of these amplified waves in this kind of microscopic resonator, this violin, this small violin for these electron waves that he's building. And you can ask, how large can the objects become? I said, well, we in principle, we're also waves, but our wavelength is so short that we can't perceive it. So how big can you go? And some of the biggest objects that people have been using to date are done in experiments in the group of Anton Zeilinger in Vienna. So he takes these big football molecules, these so-called C60 football molecules, or even now insulin molecules, and can show that they show these interference effects as well. So even for really large kind of molecules, we can see this matter wave characteristic. Okay, now I want to come back to the story of Bose-Einstein and tell you another way how we can make this wave character very prominent. And so let's think about a classical gas, the air around us. So we have the nitrogen molecules, the oxygen molecules, they all are pretty fast flying around us. And we know from de Broglie, we know what we have to do to make the wave character important. We know we have to make the velocity of the particles small to make the de Broglie wavelength very big. And velocity small means, in thermodynamics, means to cool down particles. Okay, so if you think about what is thermal motion, what is temperature? Temperature describes how fast particles move. And if you slow them down, if you cool them down, then you can dramatically enhance this de Broglie wavelength according to what de Broglie has taught us. And now comes this famous prediction from Einstein and Bose into play. What they said was that if this de Broglie wavelength becomes so large that it's comparable to the average spacing between the particles, then something magical happens. Then suddenly all these waves lock together to form one kind of giant coherent matter wave. So in order to describe this, what this means, I always say it's like an orchestra where everybody, in a classical gas, like the gas around us, everybody plays whatever he wants. Okay, so it's like total chaos. The flutes play what they want, the violins play what they want, everybody. And you cool the orchestra down, you cool it down more, you freeze it down a bit more, and suddenly they all play the same tune. Okay, there's really one temperature below which you go, and suddenly they play this same tune, and they're all kind of now synchronously. And that's what these matter waves do, and that was what Einstein and Bose predicted in 1924, basically achieving the ultimate control over matter at that point. So this is pretty much, if you compare it to light, it's pretty much this Bose-Einstein condensate for matter is what the laser is for light. So if you think about a classical light bulb, you have light coming out with different frequencies, different colors in all kinds of direction, total chaos. And the laser, we like a laser so much because laser emits light, which is this perfect continuous wave. It's a perfect wave, one beam of light, one frequency, one color, one direction, not like this light bulb, which emits all kinds of colors in all kinds of directions, so basically complete chaos. So if you want to think of it, think of this Bose-Einstein condensate for matter, what the laser is for light. Okay? So that's basically what this BC is and why we're so excited about it. Now there's one problem. If I basically take strictly this condition for Bose-Einstein condensation, where the de Broglie wavelength has to be comparable to the spacing between the particles, it turns out when I do that, I just take the density of water and I calculate when is this condition met, at what temperature. It turns out this is at 1 Kelvin. So what's that in Fahrenheit? So that's in Celsius, it's minus 541 or 42 something. Am I right? Or, okay, I know it in Celsius. So it's minus 272 degrees Celsius, very close to absolute zero temperature. But the problem is at those temperatures, water is not a Bose-Einstein condensate. At those temperatures, water is just a block of ice, like what you have in your freezer. Okay? So we have to devise new ideas, and this is what Eric Cornell, Carl Wyman, and Wolfgang Ketterle had the ingenious idea that basically if we can lower the density so that water or our gas cannot form this block of ice, but at the same time we can reach conditions for Bose-Einstein condensation, we can achieve this new phase of matter that has been predicted. Okay, but if we want to lower the density, it means we have to go to even lower temperatures. And now let me show you what we're facing from an experimental challenge where we actually have to go in the experiment. So this is temperature scale. This is this de Broglie wavelength I introduced to you. And so these are kind of typical points. You know, water freezes here, air liquefies, 4 Kelvin, helium liquefies, minus 452 Fahrenheit, degree Fahrenheit. But we need to go 1 million times lower temperatures in our experiments to reach these conditions for Bose-Einstein condensation. There simply is no fridge in the world that can take us from here to 1 million times lower than there. Okay. So we have to develop new cooling techniques to cool the atoms, and whenever you cool things, you know, fantastic things happen. We know that in nature. We know, a gas can turn into a liquid into a solid, a normal conductor can turn into a superconductor. We'll talk about these BECs in a second. Just to show you one of these magic properties of these superconductors, which is very related to the phenomena of Bose-Einstein condensation that I'm going to tell you about now in a second, how we see that. If you take such a superconductor, just to show you the beautiful physics you have, you place it in a magnetic field, it just floats above this magnetic field. Okay? And what's happening is there's actually a current running in this superconductor, and it can run without friction. It's frictionless current that runs in the superconductor that creates a magnetic field that repels it from this magnetic field and keeps it floating like this. Here's another picture, beautiful picture of how that happens. So that's actually very similar to the physics that we're going to discuss here, what happens in these superconductors when you cool particles down and they form a Bose-Einstein condensate. Okay, so what is this radical idea to cool to 1 million times lower than any other machine can do for us? And this is another great story in physics, and actually is about radiation pressure, about cooling with light. Okay. So now, usually cooling actually with laser light, as I'll tell you, and you might think I'm crazy because laser light people associate totally different things. Totally, you think welding, heating up things, blasting things, you know. But I'll tell you, you can cool with laser light super efficiently. And that you can cool with light, or that light exerts a macroscopic force onto particles, you can actually also see in this picture of the comet. This is comet Hale-Bopp, and it has its dusty tail behind it. And what you find is that actually this tail of dust here usually points away from the sun. And the reason why it points away from the sun is because, one reason is because these light particles emitted by the sun exert like a wind on those dust particles and blow them away from the sun. So light really on a macroscopic scale, you can see is exerting a force onto this comet, onto the dust particles of the comet. And if you're a science fiction reader, you might have read about these novels where people think of building spaceships with sails that are kind of propelled by sunlight, these light sails. I mean, that's, and actually there's been a recent proposal actually by Milner and come right to propel with laser light, put lasers on Earth and, you know, propel small satellites with that. Okay, how realistic that is, we can debate, but you can see that really light has a profound impact on particles, on material particles. And here's this idea that Ted Hensch and Arthur Schorlow had in 1975. What they said, okay, if light has this strong, it's like a wind on those particles, let's let the wind blow from all directions. So let's take laser beams, shine one from here, one from here, one from here, and one from here. And now we have to do a trick. We have to arrange the laser beams in such a way that in whatever direction the particle moves, it will always see more wind blowing against it than from behind. And if that's the case, then the particle is going to be slowed down. So imagine we would put you would start to run, and whatever direction you run, the wind is always blowing against you. Okay? And that would always create a tremendous friction force and slow you down. And this is exactly what we're doing with these light particles. And the people who really executed that, our heroes Stephen Chu, Claude Contanucci, and Bill Phillips, who for the first time kind of realized these laser cooling ideas in the lab. So just to give you an idea that the forces and the accelerations are really tremendous that you can achieve with light beams. Okay, let's take just a normal laser beam. Let's shine it onto our favorite atom. This is this rubidium atom, for example, and calculate the acceleration I can achieve by shining this laser beam onto the atom. What you find is that this is like 10,000 times the acceleration of the Earth that we have. Okay, 10,000 times larger accelerations than the Earth acceleration that we can experience. And that means we can cool down particles extremely rapidly to very low temperatures. We can bring them almost to a standstill just by shining laser light on them. Okay, here's a picture of how these apparatuses look like. This is one of our vacuum apparatuses. Because this is so super cold, everything inside here is microkelvin, nanokelvin temperatures. We have to have the best thermal insulation to the outside world. And the best thermal insulation is a vacuum. Okay, as you know from your cup of coffee, if you buy a good vacuum insulated cup of coffee, same thing here, but we need an even better vacuum than that. And here's a picture of this, how this actually looks like, a video. Here's a small laser-cooled cloud of atoms. So these are our rubidium atoms, around 1 billion atoms. They're like the size of a pea, floating inside this chamber. They have no contact with the outside world, just held by these light forces. You don't see the lasers. They're actually lasers coming from all directions. But you see the cloud glowing. Actually, it would glow red. There's just some filter in front of the camera recording this. And you can actually also see how slow these atoms are in the end. You see how slow this is real time, how slow they fly apart when we turn off the lasers. That means they have to be extremely slow, because if I would do that with a room temperature gas, it would fly 300 meters in the same time. Okay, so just by looking at this gas cloud, we can tell that we're dealing with extremely cold atoms in our vacuum chambers. All right, so now we have to do one final step to get to the BEC. Unfortunately, this laser cooling ideas, people had hoped it would bring them into this regime of BEC. The condition, de Broglie wavelength being comparable to average spacing, but that didn't work, so they had to invent another technique, and this technique you also know very well. Let me skip across this. And this is how you cool your cup of coffee. Okay, if somebody serves you a cup of coffee which is too hot, what happens is what you're going to do is you're going to blow away the steam above the cup of coffee, and the coffee gets colder. So what are you doing? You're removing the most energetic, the most fastest particles, which are the ones in this vapor, from the coffee system in your cup here, and thereby only the slower particles remain. And remember, the slower particles are the colder particles. That's how you cool your cup of coffee, by blowing away the steam, the hottest, the most energetic particles. And this same idea, these two MIT physicists, Tom Graytak and Daniel Kleppner, had, that we could do exactly the same thing for cold atoms. Okay, so we could cool atoms in our traps by always removing the hottest atoms in the system, letting the system kind of relax again, and then kind of remain with the cold atoms in the system. And again, I have a small. I'm happy I still found the applet because they shut down the website in Colorado, but I found the applet somewhere else. So here's how this looks like. So you have this gas of atoms in the trap. Okay, this is at some temperature, and you see there are some fast atoms, which are the red ones, and some cold atoms, which are the blue ones, which have moved faster, and they all collide with each other all the time in the system, but they're held in this container that we have here. Okay, and now we want to remove the most energetic particles. So what I can do is I can just lower this trap depth here. Okay, and now the hot ones can escape. Okay, see that? And you see how the temperature simultaneously, which is indicated by this arrow, drops. And this is where I reach Bose-Einstein condensation. Okay, so now in this game I have to, you can try it for yourself, you have to do it and reach BEC with the maximum atom number, that's what you want, which is the lower left corner. So we lower a bit more, lower a bit more, lower a bit more, lower a bit more, lower a bit more. Oops, am I going to make it? Yeah, now I made it, okay. To 17 particles, okay, you can try for yourself. And that's the idea behind evaporative cooling. This is how this works, and this is what we do in our labs basically all the time. Okay, to see these gas of atoms, one way to see them is actually to just release them from these traps. So the gas cloud now expands in free space, and then we can take a photo of this gas cloud by just shining a laser beam onto the gas cloud. Where there is this gas cloud, this laser beam is absorbed, and this absorption on this laser beam we can just, with a lens, image onto a good CCD camera and take photos of that. And these are photos like this one. And now you see this magic moment of BEC, which Wolfgang in his lab, had this exclamation mark. You see here this kind of cold cloud of atoms, this hump here, the particles flying away. This is like the velocity in x direction, velocity in y direction, and how many of these particles we have. And all the time it looks like this. All the time it looks like this. And then suddenly you hit this temperature, this one critical temperature, where I said they all now play in sync. And then suddenly you see this peak shooting up here. Okay, suddenly there's something happening in the system. You see this dramatic peak. It's really you can't miss that when you see it the first time in the lab. It's really quite spectacular when you see it yourself. And now these are all the particles in this kind of giant coherent matter wave, all in tune with each other, all in sync with each other. But okay, you'd say, okay, well, there's this peak, but what about the waves? Can we see the waves? Yes, you can see the waves now, and now on a macroscopic scale, because now you can take two of those gas clouds and do our sand experiment, right? Remember we said the sand experiment, if it's classical particles, we just add sand, and sand, it gives twice as much sand. But if it's waves, then we should have these interference patterns. And now we're taking this gas cloud and this other gas cloud, we're overlapping them, and we're taking a photo of that, and what comes out is this beautiful interference pattern. And now what I want to make you aware, this is scale now of this thing is 1 millimeter, okay? This is not anymore in the microscopic realm of atomic physics. This is really something you can almost measure with your ruler at home, okay? And it's like, I always say, this is such a fantastic experiment. I think it's like, turning your water faucet on at home, adding water from the side to it, and suddenly you see that water vanishes in some spaces and other places get amplified. I mean, you would be shocked to see that. And this is like as shocking when you see that the first time. Okay, this is how the labs look. Okay, and this is the reality. What I'm hiding from you, what we have to do to make it all work out. And, when we have the school children come to visit us, they always think this is the storage room for our optics, but this is not the storage room. This is the actual experiment, arguably one of our more complex ones. So you have this array of mirrors, of fibers guiding the light from this table to the actual experimental table. That's not even the experiment you're seeing. That's just the table where we generate all the laser light we need. We guide it over to the experimental table. Yeah. And so it's complex, but it's like we run these experiments with 4 or 5 students, so it's small tabletop experiments, as we say.
What's the distance scale there?
This is about a 3-meter table, 3 meter by 1, something like that. Yeah. So yeah, and these are, there are like thousands of elements on this table, okay, and each one is quite expensive actually. Yeah. And as I say, when I said the students when they come in, they immediately want to turn on one of the mirrors here. Yeah. So this, like for example, this is a mirror holder. There's a mirror in here, and with these knobs you can turn the angle of the mirror that we use to align the laser beam. And if you just turn one mirror here, then the whole experiment doesn't work anymore. And then the poor graduate student has to find which mirror did you turn. Okay. So that's a challenge, as you can imagine. This is this glass cell I talked about. This is, where we can hold the atoms in vacuum in the end when we do this cooling to the BEC. And what I really find remarkable, there's nothing, we don't have any kind of liquid nitrogen, anything cold. Everything is at room temperature. You can touch everything here. It's at room temperature. But just a millimeter behind this glass wall, we have this microkelvin, nanokelvin temperatures. So that's really remarkable. And even just thinking about it is mind-boggling. Okay, now let me turn to another story of how we can actually emulate materials with these Bose-Einstein condensates. And the idea of doing that is basically trying to zoom in into matter in a very new way. So here I've sketched out, and you can barely see it, that's on purpose, some crystal. And so tiny that we even can't see it almost here on the crystal on the paper. But if we could, of course, blow this up by a factor of 10,000, now we have a much easier time seeing what's going on. Okay? And that's exactly what we're doing. That's the idea of what we're doing in our experiments compared to real condensed matter physicists or solid state physicists. We're creating crystals out of light by interfering again. We're making use, you see, interference is a very important topic in my talk. We're taking two laser beams, shining them on top of each other, and what comes out is an interference pattern of light. I'll show you a beautiful one in a second, of bright and dark regions in space. This periodic pattern of bright and dark stripes in space forms a periodic crystal in which we can trap these ultra-cold atoms. Okay, so here's a picture of Ted Hensch's labs that he took that shows you this. So he took like two beams passing through these apertures. You overlap these two beams, and out comes this pattern of light. That's recorded pattern of light. You take 3, and suddenly you get this kind of crystal structure. Okay, you take 5. And it looks even more beautiful. Okay? So that's just light. That's just light interfering, just 5 beams of light interfering. And you can imagine, by interfering more complex patterns, you can generate almost any pattern of light you want. And now what we do is we can actually load the atoms into this pattern of light. And that's why we need the ultra-cold atoms, because the light field is not so strong to hold them. We need these very cold atoms that don't move too fast. We gently place them into this crystal, into this web of light, and then they are held in this crystal of light in free space. Okay? And that's our crystal. And this crystal has much larger structures, much larger scales than the normal crystal. And we can observe the particles actually with standard optical microscopes and see each individual atom. Actually, I think we have time. Let me show you this movie also. It's a nice movie of showing these optical lattices at work, again from Ted Hensch in his lab. So he takes these 4 laser beams, first overlaps 2, and looks at the interference pattern with a microscope. And you see the stripe pattern I showed before. So this wobbling about we don't want. So we don't want that in our experiments. And if you take 4, you see this kind of pattern. Also, this wobbling would not be good for us. But okay, it's here in this experiment. And now what he did, actually, you can see it will trap even more macroscopic particles. So he took like small plastic beads, dissolved them in water. Okay, these are the plastic beads in water, jiggling about. Now you just turn on the light. And can you see how they're following the light? How they're attracted by the light? Yeah. So the light really exerts a macroscopic force onto these particles. In 2D, it's even more beautiful. You see how they want to lock into the light pattern? Okay. So it's just the light exerting the force onto these particles. And this is what we make use of with the ultra-cold atoms. How we can trap them in the light bead. And we do this with thousands of atoms, with millions of atoms that can be trapped in these light crystals. And very recently, we've been able even to see each individual atom in these light crystals. So this is now a photo, and now we can take photos with this very good microscope objective of atoms held in this light crystal. So each point you see here now is not the plastic bead, but it's a single atom held in this light crystal. Okay? And you can beautifully see them with a very, very high signal-to-noise ratio, as we would say, so they're very visible to us. We can see them excellent. And you can see different phases of matter that appear. You can, atom by atom, really record what's going on in this crystal. You can see individual defects in this crystal popping up. You can move individual defects in this crystal. So you can really see on a microscopic basis what's going on in this material and how are its properties affected if I change, for example, the crystal geometry, the crystal strength, or the interactions between the different atoms. So one thing I just want to show you, when you can see these atoms, you also can control them, just to show you that we can really control them down to the level of single atoms. So we can really go into this crystal of light with the atoms in there and move the atoms around to any position we want. So we can make this box of atoms, this line of atoms, this star. Well, and as quantum physicists, we like to make the psi out of 26 individual atoms here held in this crystal. And each of these white spots marks a light crystal point. And when there's this bright fluorescence, there's an atom there sitting there as well. Okay, so now how do atoms move, for example? Let's do an experiment. I would call this the quantum horse race. How do atoms move in these crystals? So quantum particles move very different from classical particles. So we set up a small horse race. Okay, so these are our horses, the atoms. They're aligned here along a line, and then we let them move in the crystal in one direction only. Okay? So now a normal horse would run in one direction. Hopefully they all run in one direction. Your horse doesn't run in the opposite direction. In quantum physics, actually, the horses do run in both directions, and the rules of the game are even more strange. You're not allowed to look actually which particle, where the horses are, where the atoms are. So this animation is a bit deceiving because you don't know which horse is winning the race until the final moment when you take the picture. Okay? You're not allowed to look before. If you look a lot before, you've destroyed the whole race. Okay? And so we do that. So here's kind of the particles aligned up along this line. They're moving in this direction. And now we let them run. And we record after a certain time. We take a photo of where they occur. And now when you repeat this experiment many, many times, you find something actually very strange. So imagine you have a pack of runners. You do this race with the horses or a pack of runners. And usually you have very few fast runners, quite a few mediocre runners, and a few slow ones in the tail like me. And then actually these quantum particles on the lattice, they're very different, as you can see. So if this is kind of the distribution, the probability of having a fast runner, you see that actually there are a lot of fast runners running to the left and to the right, and very few ones actually coming here tailing behind. So there's actually really a large part of the very fast atoms there, which is very unusual and something we don't encounter typically in free space. But you see actually the measurement is in perfect agreement with what quantum mechanics predicts. So if I take this Schrödinger equation, which gives me this orange curve, and compare it to my histogram, this is the measured arrival time of the atoms, it's in perfect agreement and shows us we can study this motion of the atoms in a beautiful way in these light crystals. Something we're doing now is that we're really almost doing arbitrary light patterns, shining arbitrary light patterns onto the atoms. So, we're taking something like this projector there and shining patterns of light onto the atoms that allow us to generate arbitrary crystal structures, or to study, for example, what happens when atoms flow through a thin wire. How do they flow through this thin wire? How is the conductance properties changed as the particles interact differently, for example, flowing from here to here? So this would be your battery, your reservoir, where the electrons flow from here to here, and this is something now you can study in these light crystals with this microscopic atomic resolution. Yeah. You can also study kind of things you would not have thought about, and I certainly would not have thought about in the beginning. We even learned that we can study things that have relevance, usually at much higher energy scales. You heard about the Higgs particle at LHC. Actually, there are something like Higgs particles, different kind, not the Higgs particles at LHC, but very similar kind of excitations at these ultra low temperatures as well. Okay, and these particles, even they are so slow, they can behave like relativistic particles at extremely high energies. And this was really fun to learn about this, and we could solve actually a problem with this that was a long-standing problem in high energy physics, and trying to understand whether this Higgs particle would actually exist in a two-dimensional world. Something just for the end, for the fun of before we conclude with an application also for you. I told you about temperature. We talked a lot about temperature, right? Cold temperature, zero temperature. To make things even more crazy, you can also do negative temperatures below absolute zero. Okay? I'm not going to explain it to you. I'm just going to say when we did that experiment, it caused like immediate strong media reaction. I mean, it even made it into Fox News. And so, I mean, it was really absolutely crazy. And this was after New Year's. Then we were totally overwhelmed. This was after New Year. We're all celebrating New Year. And then in a few days after New Year, we have that. And there are a few actually websites explaining it quite well. And the one actually also I can recommend to you, it's also actually a good physics channel, is from our colleagues at Nottingham University in UK. They have a channel on YouTube called 60 Symbols, where they try to explain complex physics phenomena, and they also explain negative temperatures. And you looked yesterday, and what I found remarkable is almost 730,000 people looked this video and tried to understand what are these negative temperatures about. And actually, I think the only video that trumped this one was the one, what happens when you put your hand in the LHC or something. Yeah. Okay. So let me finally, to conclude, give you an application of, what is this all good for, apart from learning about how these particles interact with each other in complex ways, getting a better microscopic understanding. I want to conclude with an application which is actually very, very relevant to all of you today, and this is about clocks. Okay, so clocks have a very fundamental meaning to everything we do. Is it timing? Is it navigation? Whatever we do today relies on having the best possible clocks. Actually, every time you turn on your GPS system, well, not this clunky one anymore, you have a nicer one today, I have one in my watch here, it relies on an atomic clock in space. And one of the satellites sending precise timing signals from these atomic clocks to you on Earth, to me here. Yeah? So having better clocks actually is crucial to having better navigation, better synchronization, to having fundamental physics tests also. That's what we're interested in, of course, also. And if you think about it, what a clock is, it's really two things. It's an oscillator, something that oscillates, swings back and forth like a pendulum, and a counter. So let's say you want to define the second. How could we do that? Well, we could take a mechanical pendulum. I know it swings by once, twice, and we define, let's say after this pendulum has swung 10 times, we say that's 10 seconds. That could be the definition of the second. Okay, we wouldn't do that today because that would be a really horrible definition of the second, but that's actually how these things work. You know, we started out 3,500 years ago with the sundial. Then we went to the pendulum clocks, mechanical clocks. Then we went to quartz oscillators, faster oscillations. And we're at atomic clocks today, how the second is actually defined. These are like 9,192,631,770 oscillations of this electromagnetic radiation of one of these atoms in this atomic clock. When those number of oscillations have passed, have been counted, that's when we turn your clock by 1 second. Okay, so you need a counter to count those oscillations. Okay, and actually, it turns out today even better clocks are in the making at many institutions in the world. Of course, our national standards institutes here in the US, PDB in Germany, we have something similar in France, BNM-CIRT, are comparable institutions. And it turns out that today, actually, the best clocks, and this is transparency from my colleague Jonier in Boulder, are actually made by holding these atoms in these light crystals. So these atoms are now our pendula. Their electron clouds can be set into motion. And in order that they not perturb each other, that they don't collide with each other, we like to keep them apart from each other, but we like to hold them very gently. And that's what these light crystals can do for you. Okay? So today, June's best clocks are built by loading such atoms in optical lattices. And I think in the very few next years, we will see a redefinition of the second being defined by atoms held in these light crystals. So then you can say, okay, I know what these light crystals are about, hopefully. And how good are these clocks? These are tremendously good clocks. Just to give you a number, and I'll put this into perspective in a second, they have what we call uncertainty now of about 10 to minus 17, 10 to minus 18, the best clocks that we have today. And this means actually that such a clock, if we would have set it in motion at the beginning of the universe, 15 billion years ago, it would just have an inaccuracy today of 1 second. It would lag by 1 second. That just tells you how good these clocks are. Okay. And, well, we don't know what they're going to bring us, but I think they're going to bring us many advancements in science and technology, and this is all happening in these light crystals that I told you about. All right, this is where I want to end my talk. I hope I gave you an overview, about the exciting physics of quantum simulations with ultra-cold atoms, in my case, how we build these, some of the phenomena we're looking at. And this really ranged not only over condensed matter physics. I told you about some applications in high energy physics that are colleagues approaching me, whether we can't do black hole models and things like that in these cold atoms. So they're really serving as fantastic test beds for really trying to understand, how matter behaves, how collective matter behaves, how these particles interact if we expose them to kind of new environments. And you see, we have really very flexible environments we can expose them to that we can't expose normal materials to, normal particles to. Okay, with that, I would like to end, and thank you very much for your attention.
Questions?
Let me get the microphone.
What kind of power level are you using in the lasers? Specifically, how much wattage are you really using on those?
Okay, so for the light crystals, it depends a little bit how deep we want to make these lattices. Sometimes the more the better. So typically it can be up to 50, 60 watt. Which is not super strong for a laser. I mean, it's dangerous enough that you want to wear your safety goggles. Let me put it like that. So it is dangerous. But it's not like, people who do high power lasers would laugh about these power levels. No, because you see, because they're so cold, that's the nice thing. Because they're so slow, they're so cold, we don't need such deep potentials to trap them. Even more gentle potentials are sufficient to hold them in space. Yeah.
In your laser cooling system, how do you sense the direction those little buggers are moving? And since they're a cloud, surely they're not all moving in the same direction at the same time, at least in the beginning.
Absolutely. So yeah, both absolutely very good questions. So first of all, you're absolutely right. They're moving left and right, up and down, and it's a cloud of atoms. So you have to arrange it such that whatever the atom does, it's always seeing the wind blowing against it. And the way to do that is through the Doppler effect. Okay, so what you actually do, so it's a bit more, what you actually do is let me come back to this image and show you what we're doing, that this works. Okay, so you have these lasers, and usually, let me draw a sketch here. So you usually have an atom, and simplify the atom, let's say, has two states. And when a photon comes and interacts with the atom, this photon can get absorbed and excite the atom to an excited state. Okay, so typically we match the energy of this photon to this energy separation here, so that it can be efficiently absorbed. But if it's kind of slightly what we call redditune, if the frequency of the photon is slightly below the absorption frequency of the atom, okay, what can happen is that then in that case, actually, if the atom moves, let's say the atom is moving in this direction, this frequency of this beam is slightly lower than is needed to actually be absorbed. If I move in this direction, I have a Doppler effect, which shifts my frequency up. Okay, so what the atom sees is actually the right frequency, but only because when it's moving in that direction. Okay, remember, let me show you. Actually, we'll go back to our ripple tank to show you this Doppler effect. It also has the Doppler effect. Where's the Doppler effect? Here. Okay, so you see you have a moving atom that emits waves, and depending on whether you're going in the forward direction or the backward direction, you see the wavelength seems to change. Okay, so this is now a moving emitter, and the wavelength shortens in the direction where it's propagating and lengthens behind. And this is what we're making use of. So we're making use of a clever trick that, in that direction the atom is moving, it sees more kind of light now in resonance, what we say, which can be more absorbed now, so the wind is blowing stronger. So I'm not sure. Okay. Okay.
That's why we got the Nobel Prize for that.
Yeah.
Could you do something like the analog to the Josephson effect?
Oh yeah, absolutely, absolutely. That's what people do. So, for example, if you want to have a thin barrier, for example, where you want to study, make a Josephson junction, what you can just do, you can, for example, shine a line of light like this one. Like this one. This is now light, a line of light, but it's a potential. We said light is like a potential for the atoms. So this is like a very thin barrier. And you could put a superfluid, a BC to the left of it, and a BC to the right of it. And if it would be classical particles, this would be just a wall, and the particles can't move through the wall. But in quantum mechanics, you can move through a wall. Okay, that's what we call tunneling. That's for something else that's amazing in quantum mechanics. And then you can connect them, and you can connect this, for example, with this thin light wire. And people have been doing that, yes. Mm-hmm.
You mentioned that you were using polystyrene atoms. Is that the material you've had the most success with? What kind of atoms do you usually put in there?
No, so the polystyrene, these were just the plastic beads that just
right.
for illustration purposes
okay.
showed you how the light forces work.
Right.
Okay, so what we're using, what we like to use, I mean, people have been using atoms all around the periodic table. But mostly what works nicely are alkali atoms in the first periodic group. So we like lithium, sodium, potassium, rubidium, cesium. Why? Well, there's a reason, because they have a very simple electronic structure, and we have very efficient lasers. There's actually a purely technical reason. We have very efficient lasers that work at those wavelengths. For example, just for example, rubidium was great. We like rubidium because all the CD writers, when they were still used, nobody uses them today, but CD writers, mass market, high power laser diodes available, exactly at 780 nanometers. That was just a coincidence, okay, that they made them at that wavelength. But that was great for us because we could buy cheap lasers for $50. We could have our high power laser, right? But now they're not produced anymore, so we have to stock up on the remaining 780 nanometers diodes. And then the Blu-ray was the same thing. Blu-ray diodes also then was good for lithium, so it was kind of a pure coincidence. Yeah.
And you see them optically because you move them so far apart using the light waves.
That's right. They are separated at micrometer distances or half micrometer distances. So with a good microscope, you can see them. And this distance is about 10,000 times larger than what atoms are spaced in a normal crystal. So in a normal crystal, you could never use normal light.
You need electron microscopy, which destroys the setup.
You use electron microscopy, or you need a good X-ray source, a very low wavelength microscope, and that people are building those. But these are expensive machines, and they have limitations. And what's nice here, that we can really see this with optics. And also, what I didn't say, next to enlarging the length scales, at the same time, all the time scales become extremely slow. So everything that happens very fast in a solid is slowed down dramatically in our light crystals. So looking at the time evolution of what's going on is much easier for us. It's actually trivial for us than for a solid state physicist trying to do that in a real material.
Thank you.
I have a couple of questions that are going to reveal. Oh, really?
I'll be there afterwards, so you can ask me all your questions afterwards. Don't worry.
So the first, I guess, then I'll bring it down to my level. The things you have with lasers and being able to move atoms with the force or the attraction of light or the pushing of light and things like that. Can you describe how that could be used to create like a Star Trek transporter?
Oh, no. No. I think that's a simple answer. I mean, the only thing I can explain is what these, there's these ideas of propelling spaceship with these sails, light sails, and people have been seriously calculating this, not just science fiction. I mean, people have been thinking about this. I mean, maybe Lars, you know better than me, but I just know this recent Milner proposal to actually propel small satellites, have small satellites that are spent in space, and you want to have laser cannons here on Earth that shoot up the light beam towards that satellite to propel it. But I think it turned out that you need a lot of power actually to do that, and many lasers, so I'm not sure it's realistic, but something to think about. So you can propel things by light. Yes, you can propel things by light, for sure. Yeah, I've shown you. Yeah.
Human atoms, why can't you do the same?
Human atoms? Oh, you probably would be heated up before you're propelled a little bit further on. That's your problem. Yeah. If you put a good reflector on you and maybe put you a lot of power. No, you can. I mean, you can levitate. As I showed you, you can levitate. And there's a nice experiment we always do, and you can levitate particles in a laser beam. But usually, it gets scales unfavorably the more massive you become, unfortunately.
So, man, could you tell us a little bit, give us a sense for that optical table. You have many of those in your lab.
Right.
When you start a new experiment, somebody has to lay that out.
Yeah, so typically when we start, of course, there's nothing in the lab. These are empty labs. There's absolutely nothing. And we have to build all the electronics. And that's, as I said, that's not even the experiment. That's just a preparation table to prepare all the light beams. You see these yellow cables, they're glass fibers that guide the laser light from this table to another table where the actual vacuum chamber is, where we do the laser cooling and the light trapping and everything. Yeah.
So what's
yeah, go ahead.
Amount of time?
Yeah, so amount of time, typically 3 years to get this going.
With 5, 10 people?
Yeah, 5 people. If you're lucky. If you make an error, 1 year more.
Right.
Yeah. How many atoms can you hold at a time at this point? And how long can you hold them?
Yeah, good question. So we do this ranging from few atoms, even down single atoms, up to millions of atoms that you can hold in these light crystals. How long do you hold them? Well, you can hold them tens of seconds. Okay. So that's plenty of time for everything we want to do.
What happens after 10 seconds? They fall apart, the whole thing?
Yeah, that's a good question too. They typically heat up. Eventually, they do heat up, and they boil off. Essentially, they sense that the environment is not really, and the laser beams around them are not really letting them stay cool as we would like them. Yeah, exactly. But 10 seconds really, that's, I mean, a really enormous amount of time for us to do experiments. Absolutely. So there's plenty of time. We're absolutely not limited by that 10 seconds. But then, when that happens, or when we even take a photo, we have to go through all the cooling cycle that I told you again. We start with a hot cloud of rubidium atoms. We do laser cooling. We do evaporative cooling. We load them into a crystal. We let them evolve. We take a photo. Bang, gone. Again. So that whole process takes about 20 seconds, 20 to 30 seconds. So every 20, 30 seconds, we can take a picture. Yeah, sometimes 24/7. Yeah. That's what we try to keep it running as much as we can, to get as much data as we can.
You are, in order to see the individual atoms, I assume you're fluorescing. Is that correct?
Mm-hmm.
And is the recoil enough to disrupt the crystal?
Okay, that's a very good question. Yes. So what the question is, when these photons hit the atoms, so the atoms light up. That's how we see them. But they also give a kick to the atoms. That's what we talked about, right? That's the mechanical part of the interaction. So that's indeed a problem. And what we have to do, that they really stay in place, that they really stay put. Now, we want them to light up. What we want of the atoms to do when they're in this crystal, we want them to light up to show themselves what they're doing. But at the same time, we don't want them to move during this illumination, because that would falsify their original position. We want them to stay put and just light up, okay, where they are, and reveal their position. And to do that, we actually have to combine laser cooling and fluorescence. So we have to cool them simultaneously while they fluoresce, so that they stay low enough in temperature so they can be held in place by the light crystal. And at the same time, we turn the light crystal power up as much as we can, and that comes to your 60 watt. That's why we like the 60 watt lasers. Then we really crank up everything we have at that point when we take the photo, because they kind of get hotter. Mm-hmm.
I was just wondering what some of the other applications are. I know you'd started the talk with quantum computing. Is that another application beyond?
Well, we're not. You see, quantum computing is, in a sense, is a more even advanced form, I would say. If you have a quantum computer, you can do quantum simulations with a quantum computer for sure. It's more universal, but it's something much more complicated. Yeah. Okay, much more complicated, and people working on that, but I think many are now turning towards quantum simulations because we see we can solve problems, or physics problems also in biology, maybe problems in other fields of sciences already now with the systems we have. So why not do that? Okay. And with the quantum computer, there are only a few algorithms we actually know which would benefit from a quantum speed up. Some of you've heard about number factoring, for example, Shor's algorithm. There are not so many algorithms we actually know which could give us really a advantage of a quantum computer. So I think actually, in a sense, Feynman's original vision was correct, that there are actually much more applications in the sciences for these machines. I mean, this is never going to be your word processor where you're going to type, things on, for sure. Yeah.
On that note, let's thank Immanuel. So we do have refreshments in the courtyard, and I'm sure Immanuel will be here to continue to answer questions. So good evening.